Okay, so today I'm going through ISP task 2 on waves and light, which, if we scroll down, is talking about energy levels, essentially line spectra, and a transition between discrete energy levels, and we need to get our head around that idea. So let's jump straight in with the Explaining Everything task. I've got a PowerPoint from the lesson nearby. Remember that all of these are available in the VLE if you wish to find them. So, using a diagram, show how absorption or emission of photons can be shown using an energy level diagram. Explain how we can calculate the wavelength or frequency of a photon, including the equation. So, let's go for the second part of that first. We've got the wavelength or frequency of a photon. So remember, frequency is E equals HF. Pretty nice and straightforward, but remember F from the previous video, the frequency is also equal to wave speed over wavelength, and that comes from the idea of the wave equation. Okay, so it's just a rearrangement of that, gives us this one over here. Now, if we're talking about a photon, we're talking about the speed being the speed of light, so you end up with C over lambda. You can sub that into there, you end up with E is equal to hc over lambda. Now remember, this equation is not given to you in the exam, so it's something you do need to be able to derive and actually use if you're after the wavelength. Frequency is straightforward, wavelength slightly trickier. Okay, so now they want us to actually talk about a diagram, use the idea of electron volts and absorption and emission. Okay, so electron volts, remember 1 electron volt is a unit of energy, so that's 1.6, right? Times 10 to the minus 19 joules is 1 electron volt. Okay, so we use that as a unit of energy. It's because the energies we're talking about in this situation are very small. So if the energies are very small, we want to use a unit that allows us to explain, allows us to compare things that are very small. So if we use a unit like an electron volt, it's easier to compare than trying to compare very small numbers of that size. So let's get stuck into some energy level diagrams. So remember, these are the calculations we actually did in class. So if you look at them again, you can, and have a go at them again. Remember, the answers are there for you to see. But here we have some energy level diagrams. Okay, so if I make this full screen, and just move the webcam out of the way for a second. Okay, so you can see that these are all transitions leading to the emission of a photon. They are losing energy going towards the ground state. Remember, ground state is negative, 0, the ionization, or this is where you need to get to for ionization. Remember, so the ionization energy of this atom would be 13.6 electron volt. Remember, look at the unit carefully. Sometimes they'll write times 10 to the 19 here rather than electron volt. So look at what unit they've given. So these are all different transitions. All of these are completely different to each other, and they all lead to emission of a photon. And remember, the energy of that photon is going to be dependent upon the difference in energy levels. Absorption, the arrow would be going the other way, okay, and the amount of energy absorbed would be equal to the difference between the energy levels. Remember, it can gain more. Okay, so if this gained, say, 10.4, okay, so 10.4 would take us to minus 3.2 over here. It will drop back down, and that 0.2 difference would release a photon of energy of 0.2 electron volts, of which frequency you could calculate as it dropped down onto this, and then it would fall back down to the ground state afterwards, releasing again another photon. Right, so every time the drop down happens, photons are released. Okay, that's the explaining everything sorted. Very, very straightforward, very, very easy explaining everything. A large amount of space, you can draw the diagram clearly. Let's get stuck into the questions. There's the photoelectric ones from last time. So here we go, task 2. So diagram shows some energy levels of a tungsten atom. An excited electron, so excited means, remember, it's being given energy. So an excited electron falls from the minus 1.8 kilo electron volt. Okay, so kilo, key point there, times 10 to the 3. Let's have that on the side. To the 69.6 kilo electron volt. 69.6 kilo electron volt. Okay. Again, so we've got the idea of a times 10 to the 3 in there. Level. Show that the wavelength is approximately 0.02 nanometers. So we're going to show 0.02 nanometers. Nano is times 10 to the minus 9. Okay, that's the idea there. Right, okay, so let's figure out the energy difference first. Our change in energy is going to be equal to hc over lambda as we've got from before. Now those two are both constants, remember, and that is the wavelength that they're actually after. So let's figure out our change in energy in electron volts first, and then convert that into joules. So my trusty old calculator. So the change in energy. So 69.6 take away 1.8. So that gives us 67.8 kilo electron volts is our change in energy. So 67.8 kilo electron volts. So now let's convert that into joules. So the first thing we need to do, is do that as times 10 to the times 10 to the 3. Answer EXP3. Didn't like that. Okay, so 6.78 EXP3. But now we want to multiply that by the fact is 1.6 times 10 to the minus 19 is a charge of is a value of 1 electron volt. So that gives us about 1.08 times 10 to the 15 joules. So 1.08 times 10 to the 15 minus 15 joules. Very small energy. Sounds about right. So now we've got our energy. We can figure out our frequency. So these two just swap places in terms of the equation. So wavelength is therefore equal to Planck's constant times speed of light divided by frequency. So let's put that through. So that's 6.63 times 10 to the minus 34. Let's put that there. Multiplied by 3 times 10 to the 8. Okay, so that's the top line. Now we need to divide that by our energy. So that's 1.08 times 10 to the minus 15. Okay, so you end up with about 2 times 10 to the minus 10. Which therefore gives us about 0.02 times 10 to the minus 9. Yeah, so we've got the correct answer there. Let's double check our working for that one. That's gone slightly too far. So there we go, conversion to electron volts, figuring out our energy, which seems slightly different. Am I looking at the right question? No, I'm looking at the right question. Oh yes, we should have got minus 11. So probably a small error in my conversion of energy over here that I've done. Because I've got minus 15, it should be minus 11. Oh no, hold on, that is the energy. Oh no, sorry, that is the final answer. So yeah, we were slightly off by a power of 1. I probably made a mistake while typing in a value. So just if you follow this through, you can see clearly any mistakes that I might have made. They've got a slightly different method. They do equals HF, they figure out the F, then use the speed of light to figure out the wavelength. So you can use that method. So I probably made a small mistake there. But you can follow that through yourself and find that. Probably a calculation error. So if you show all your method like I have in the exam, remember the examiners would give you the full mark for that because it's just a calculation error in terms of pressing the wrong button on the calculator. Which part does this belong to? Well, it's going to be a very short wavelength, so therefore it's a very high frequency. It's going to be X-ray or gamma. Straightforward as that. Next. So, line spectra. Okay, so when we're talking about line spectra, we're talking about the idea of certain frequencies of light either being absorbed or emitted. That's what line spectra is about. And when you're looking at stars, these gases have specific elements in them that absorb these frequencies of light. Okay, so let's see what the mark scheme says about line spectra, what specifically they're after from us for line spectra. So light in this wavelength is absorbed by hydrogen, okay, in the outermost layers of the sun. So absorbed radiation is re-emitted in all directions, is the idea in terms of absorption lines, and that's not the question we're actually being asked to answer. We're actually asked to answer the one on line spectra. Here we go, not having the best day so far. Specific frequencies of wavelengths related to either absorption or emission, just like we were discussing, and you end up with narrow bands of wavelengths that are actually absorbed. Okay, so those are those dark lines. So next question, we've got it down here, it shows it neatly in the mark scheme. He's explained how line spectra provide evidence for the existence of energy levels inside an atom. Some of the photons are what actually being released here, and they're related to specific energies, which are therefore related to specific transitions, and these energy levels are discrete. Okay, so they're set energy levels. Okay, next one is question 8. So, state the ionization energy for an atomic hydrogen. Okay, so the ionization energy is going to be minus 13.6 electron volts. Okay, so you can convert that into joules if you wanted to. No need to do that. Okay, account for the labeling of the energy levels with negative numbers. So remember, we're talking about the fact that it's that the ground state is the lowest energy state. Okay, so that's part of the reason why we end up with minus numbers. I'm just checking the value of the ionization energy. So there you go. So we've got it over there. So remember, they've got negative numbers because you need to actually apply energy to raise it from the ground state to get it to zero. So therefore, it must start negative. So that's exactly what the first point is saying there. And the idea that the ground state is the lowest energy state. So that's the first point that I said that would have got both marks. Okay, so the electrons must be must be less than zero, i.e. negative, for them to exist as they are. The work or energy is given out to when electrons move from the ground state. So energy is now less than zero. So if they're moving away, if they're moving to the ground state, okay, they're giving out energy. So therefore, it must be less than zero, the amount of energy that they have. Right. Next question. Calculate the wavelength of a photon emitted when an electron moves from minus 1.5 electron volts to 3.4 electron volt energy level. So again, you're looking for the difference between those values. Okay, so we've got 3.4 take away 1.51. Okay, which gives us energy change in electron volts of 1.89. So now we need to get that into joules. So that's times 10. It's 1.6 times 10 to the minus 19. Okay, so that gives us how many joules is released as part of that. So remember, we need to do a HC divided by that to actually get us to our final point. So 6.63 times 10 to the minus 34 multiplied by 3 times 10 to the 8. Close the bracket, divided by the answer to the previous bit, which was the energy. So that gives us a wavelength of 6.6 times 10 to the minus 7 about. Let's have a look and see what we get for that. Let's move my webcam out of the way. Sorry, you couldn't see any of that working out. There's my final answer. You can see if you go across the top, there's 6.63 times 10 to the minus 34. And if I go across, multiplying that by the speed of light, and then divided by the answer to the previous part, which was converting this energy change as 1.89 into joules from electron volt. So let's go down to the bottom of the mark scheme. Okay, so there we go, 6.6 times 10 to the minus 7. Brilliant, no mistakes this time. Oh, well, I've got minus 6 here, minus 7. It's just going to be, you can see they've got a range over here. Minus 6 is what they're after. Sorry, I've got minus 7, they've got minus 7, but 6.6, we've got 6.57, so 6.6 is fine in terms of rounding. Exact same layout as what we did there. So there's that change in energy, there's the multiplication to get it into electron volts. So there's a question, the next one over here, I'll just read it directly from the mark scheme. So production of line spectra of atomic hydrogen in a lab. So to do that, remember, you need to get line spectra, you need to apply white light through some form of gas. Okay, so if you want hydrogen, you need to put the light through hydrogen. So essentially, if you have a hydrogen discharge tube, okay, what you could actually do in that situation is actually give out, excite the atoms inside hydrogen, and therefore they give out light. So the way you do that is you put hydrogen across a very high voltage. That accelerates those atoms in there, gives them energy, and therefore they give out frequency. If you want to look at it in a bit more detail, remember this idea is called spectroscopy, as we discussed in class, and that's what you need to use, a spectrometer or a spectroscope, to actually see these lines. Okay, so the lines you'd see would look like this. Okay, so a few vertical lines on a background, and the idea is they're not equally spaced. Okay, next question. Sketch really supposed to see, we're just doing that there. Brilliant. Next question. Okay, so below is a simplified diagram of hydrogen. Okay, so you've got the ground state, the first excited state, and the zero state there, so you can figure out the ionization energy if required. Right, so remember they're going to have kinetic energy afterwards. That's this extra energy they have when they fall back down in terms of as a result of moving from one to another. So a free electron comes in, got 12 electron volts, so we add 12 electron volts to whatever it collides with. It collides with an atom of hydrogen. As a result, the atom is raised to the first excited state. If it's raised to the first excited state, it must have come from the ground state to get there. 12 added to 13.6 minus 13.6 add 12 is going to take us to 1.6, so we're going to be on 1.6 is where we're at to. Calculate the kinetic energy of the free electron in electron volts after depletion. So starting here, minus 13.6, add 12, minus 1.6, so it is a difference that there's going to be as it falls back down, and this difference is in terms of kinetic energy. So we're looking at that as, with the calculator, 3.4 minus this one, so divide, minus this 1.6 that's on. So that's 1.8, so the difference is 1.8 electron volts is what we're looking at. Calculate the wavelength of the photon emitted when the atom returns to the ground state. So again, energy difference from there to there, okay. They want the wavelength, okay. So if you've got the energy difference, times that by 9.8, times that by 1.6 times 10 to the minus 34, okay, and then do H times by C divided by that. It's so straightforward, run that 3 or 4 times. Please practice that calculation. Okay, there's 5 marks overall for those 2 questions that are very quick and easy, as we've just gone through there. Let's clarify we're using the right methods by looking at the mark scheme. If you need to play that back to make sure you understand what I was saying, then please go through it again. So, question 9. Okay, so 1.8. Okay, that's exactly what we said. Remember the difference in energy levels, okay, is what we're looking at. And again, use this idea of E equals HF and C equals F lambda. So you've got it over here. So the way you can do it is E equals HF or E equals HC over lambda, which is the way that we're doing it. So there's your H and your C. There's your change in energy, so 10.2 as it drops between the first excited state and the ground state. Times that by 1.6 times 10 to the minus 19. To get that from electron volts into joules, and that tells you the wavelength. Okay, so again, that's quite a small wavelength, not to the level of excuse me, not to the level of X-ray or gamma, but not too far off. Okay, so I think we've got one more question left, and then we're finished on energy levels. And I've gone through this one quite quickly, so do play it back if you need to. Yep, it's only question 10 left. Scroll back up. Okay, so let's move this over to this side. So diagram shows the lowest 3 energy levels of atomic hydrogen. Excited hydrogen atoms can emit a wavelength of 656 nanometers by means of suitable calculation determining the transition by which is responsible for this emission. Okay, so this is slightly different to the way we've done it before, but it's the same equation, time and time again. E equals HC over lambda. So often that comes up. Okay, H and C are constants. However, our lambda has varied, and this time it is 656 nanometers. Nano times 10 to the minus 9. Okay, so we whack that through, figure out our energy that we get. Our diagram is in electron volts, so we need to divide whatever we get by 1.6 times 10 to the minus 19, and that will tell us the change in energy, and therefore the transition that could cause that change in energy. So let's have a look. So 6.63 times 10 to the minus 34 times by 3 times 10 to the 8 equals, divided by 656 times 10 to the minus 19. Okay, so there we have our amount of energy. We want it in electron volts, divided by 1.6 divided by electron volts, so I can get it into electron volts, so I can figure out a transition. So we're looking at a transition of about 1.9. The only transition that is 1.9 is from level B to level C, or from level minus 1.5 to 3.4. Now we need to figure out which direction it's going. Its emission must be going down. There we go. 4 marks. What a lovely question for 4 marks. Genuinely lovely. You should be begging for something like that. People make mistakes with that sort of question. You guys won't. Let's have a look. 10. 1.59 electron volts is the value. So there you go. You got your transition there from minus 1.5 to minus 3.4. Okay, so pretty straightforward. I'll just bring it up so you can see it a bit clearer. Okay, this is the idea that you should be using time and time again. For 4 marks is very, very straightforward. Okay, 4 marks is very, very straightforward. 10. There we go. So spectrum, the spectrum of light from the sun contains dark lines at that wavelength with reference the energy level diagram. Explain how this line is produced. You may be awarded mark for clarity answer. Okay, so essentially we've got hydrogen around the outside of the sun, and if it's got dark lines, that's absorption. Bright lines is emission. So it's absorbing energy levels is absorbing photons of this wavelength. So that means as the photon comes in this wavelength, it causes the electron to move, and as it drops back down, it's emitted in all directions. Okay, so that means it's not picked up by us. Okay, that's the idea. So these transitions between these energy levels take place because, or between the levels that we said, so it's minus 1.5 to minus 3.4, take place because it's absorbing photons of this wavelength, okay, and then re-emitting them in all directions, so they're not picked up by us, therefore we just end up with a dark line. Let's double check that. Okay, so light of this wavelength is absorbed by the outer most of the sun, it's absorbed and re-emitted in all directions. Okay, so that's that transition we talked about from B to C. Right, final point on here. Final question. Okay, in the spectrum of light received from a galaxy, the line appears at a wavelength of 695. So it's changed, the wavelength's got longer. How can we deduce that this galaxy is receiving from Earth? Well, it's the idea of the redshift. Okay, so the wavelength is increased, so the redshift has actually caused that to happen. So a longer wavelength has happened because it's redshifted. Remember, the redshift is the observed change in frequency due to relative motion. Okay. Excellent, guys. So that's ISP task 2 of Waves, Unit 2 complete.